The title of this talk is Policy Carrying Data, a privacy abstraction for attaching terms of service to mobile data. This talk has been presented at HotMobile 2015, a workshop that took place in Santa Fe, New Mexico. My name is Stefan Soroyo, and I'm a researcher at Microsoft Research in Redmond, Washington. And this is joint work with my colleagues, Alec Wolman and Sharad Agarwal. Mobile users face a privacy crisis. This is because the privacy landscape is very one-sided. Cloud providers control how data is stored in the cloud, how it is managed in the cloud, and how it is used in the cloud. Users, on the other hand, are at the mercy of cloud providers. They basically have two choices. Choice number one is to use the cloud and lose control over their data. The other choice number two, is to take their privacy seriously and basically to stop using the cloud. Unfortunately, neither of these two choices are terribly attractive. There is even more bad news for privacy. The cloud often has to partner with third-party providers that offer ad networks or sort of performance and testing optimization and monitoring services. Also, there is growing evidence that governments have started to put tremendous pressure on cloud providers to share their customers' data. Now, the research community and industry has long known that we have to build systems that provide strong privacy protections to mobile users. And there is a lot of work in this area with various approaches, from things like homomorphic encryption to things like verified software used in operating system and hypervisors. Our paper actually discusses many more approaches, all trying to sort of protect the privacy of mobile users. Now, all these previous approaches are fundamentally based on one approach. All these previous works are fundamentally based on one approach, and that is to raise strong fences, protective fences around their data. In this talk, we propose an alternative to building systems with strong privacy protections. We advocate a much simpler approach. Let users attach terms of service to mobile data before uploading it to the cloud. For example, like in this scenario here, in this snippet right here, this is a GPS reading uploaded by a user that contains a latitude and longitude. And the idea here is to include into these GPS readings a terms of service clause, TOS, shown right here at the bottom. In this example, the clause specifies a date retention limit and the name of a service. This GPS reading can only be used once and only for a service called Bing Maps. Historically, terms of services are legally binding. The owners of the data can take legal actions upon detecting violations of the terms of services. The key distinction here is that we propose the users to assign the terms of service and not the cloud provider. Here's an animation how our abstraction called Policy Carrying Data works. The mobile users on the right-hand side wants to upload a GPS reading to the cloud. This reading is put inside of an envelope. The envelope is a digital envelope that also contains the terms of service. In this example, the terms of service say, please do not store my GPS reading. And this digital envelope is sent to the cloud. We need two guarantees from this policy carrying data, this PCD abstraction. First, PCD must force the cloud to interpret the policy before accessing the data. And second, this interpretation, this step number one, has to be externally verifiable. There has to be a publicly available record of it taking place. Like I said earlier, solutions today, all current solutions, they attempt to raise strong fences around the data. From a technical perspective, these solutions offer stronger guarantees than PCD. So on the left-hand side, we have the current solutions right here, and the right-hand side, we have the PCD right here. So from a technical perspective, protective fences offer stronger technical guarantees than PCD. On the other hand, from a contractual perspective, we believe that PCD is stronger, and I hope that this talk will convince you of that. One more thing I would like to add to just make sure there is no confusion about this. Our abstraction PCD doesn't enforce the detection of the violations of terms of data. It's just a mechanism to attach the terms of services to a piece of data. This is the outline of my talk. I just finished telling you about the introduction. Then I'm going to tell you about the terms of services and give you a couple of examples. Then I'm going to tell you about PCD this new abstraction that we're offering, how it works. Finally, I'm going to talk about performance-related work and conclusions. So next on to terms of services. Here are some examples of terms of services. For example, users might want to specify that the credit card number should be used for a single transaction only and not be stored. Another example is to specify that no detailed processing of a photo's content is allowed. For example, if I upload my photos to Facebook, I would like to ask Facebook not to subject my photos to face or object recognition. Finally, I would like to not share any of my health data with any third party when uploaded to the cloud. On the bottom, you have more examples of terms of services. So you might wonder, what's the difference between the top and the bottom examples? Well, the top examples are sort of simple and aimed at the average mobile user, are things that we believe the average user would actually relate to. And the bottom examples are things that are a little more sophisticated, that are aimed to the sort of technical privacy expert. So for example, with PCD, you can specify data retention policies, data shareability policies, and data anonymity policies. You can specify what type of software or hardware or sort of physical compliance mechanism would you like to have on the server storing your data. For example, you want to ensure that the servers run the BitLocker software and they're equipped with TPM trusted hardware chips, and that all servers are actually located in the United States and not in some other foreign. Our solution is similar to how valuable data is treated in other cases. For example, routinely websites publish terms of service on how their users must treat the website's data. Programmers often attach licenses to their code before releasing it into the public domain. The DVD industry is forcing all DVD buyers to watch a short "do not copy or you'll go to jail" preview before watching the movie on the DVD. At this point, you might wonder, how about the complexity of the policies? Many of these previous examples use complicated policies that are very hard for an average user to understand. To mitigate this issue, we believe we can color code the policies. For example, a green policy is very permissive. The cloud can have a liberal use of the user's data, whereas a red one could be very stringent. Finally, we believe there are incentives for third-party detection mechanisms to arise. There is an opportunity for an industry, for a privacy cottage industry, to help users detect and monetize privacy violations. So I finished telling you and showing you examples of terms of service. Next, I'll tell you about policy carrying data, PCD, these new abstractions we are envisioning. Like I said earlier, our PCD offers two requirements. The cloud must interpret the policy before accessing the data. And second, there must be an externally verifiable record of this step. Our first observation was to use encryption. The key idea here is to use the policy as an encryption and as a decryption key. Don't worry too much about the mechanism of how to use a policy as a key. The point here is sort of to illustrate how the use of encryption can actually get us closer to accomplishing the PCD goals. The mobile device on the right takes the GPS reading and the policy and uses the policy to encrypt the GPS reading. For simplicity, let's just imagine that what the user would do would XOR the policy with the GPS reading and create a blob. This blob would then be transmitted to the cloud. The cloud now has to use the policy again to XOR the blob in order to get access to the GPS reading. So the two XORs, the two policies would cancel out because of the semantics of the exclusive OR operation, and the cloud would actually now be able to use the GPS reading. However, this simple scheme has two problems. One is that it can cast doubt whether the cloud really interprets the policy. Well, at the end of the day, on the previous slide, what we saw was the cloud using the policy to XOR a blob, a bag of bits, and to retrieve the user's data in that way. Does this mean that the cloud really interpreted the policy? So we started thinking about this question, and the question got deeper very quickly. What exactly, from a legal standpoint, does it mean to require a cloud to interpret a policy? In any case, we felt that this previous example, this sort of strawman design, doesn't meet this requirement. The second problem is that it clearly does not meet requirement number 2, which is to have an externally verifiable record of this interpretation. Instead, we decided to use a more sophisticated encryption scheme called attribute-based encryption, or ABE. The goal of this slide is to give a brief overview of how ABE works. Don't worry about PCD yet. The goal here is to briefly understand how ABE would work. So with ABE, there is a privacy authority. That is, there is a third party that would externally verify the policy interpretation in PCD. So you might wonder, who is this privacy authority? Well, we can imagine an organization like the EFF or the Guardian, or some sort of a third party whose goal is to keep a record of the promises the cloud makes. The cloud now has a list of attributes, such as, yes, we're going to offer the ability to only use a GPS reading once and only for Bing Maps, or yes, we're not going to store your credit card numbers. Now, this list of attributes are sent to the privacy authority, which in exchange send a set of decryption keys to the cloud. There is a direct relationship between the list of attributes being sent by the cloud to the privacy authority and the nature of these decryption keys. The privacy authority would also send a public key to the mobile device. Now, there are a couple of things I want to mention here. First is that this entire key setup is a rare operation. So for example, it can only be done once, or in fact, it has to be done only in two conditions. Condition number 1 is that the cloud changes the list of attributes, and therefore it needs new decryption keys from the privacy authority. Or case number 2 is that the privacy authority, for some reason, decides to rotate the keys and decides to rekey everyone. Nevertheless, this key setup is a rare operation. Now with ABE, encryption is done using this public key and the policy. So the mobile device will take the public key and the policy and encrypt. And decryption is successful if and only if the attributes satisfy the policy. This is the key property that ABE gives us, which is that the attributes must satisfy the policy for the decryption to be successful. If the attributes do not satisfy the policy, for example, the user says something that the cloud never declared, then decryption fails. So how does PCD works with ABE? Well, the mobile device takes the GPS reading and encrypts it with ABE with a policy that says, for example, do not store. That's the encryption step. This blob is then passed to the cloud, which attempts to decrypt with its keys. And decryption is successful if and only if the attributes satisfy the policy. We believe that PCD meets the requirements that we put forward, and this is because ABE, attribute-based encryption, this encryption scheme we're using, forces the cloud to declare the attributes offered in exchange for the decryption keys. Because of this, the website must be able to declare that it satisfied the mobile user's policy before accessing the data. And also, there is an externally verifiable record of this because that is stored by the privacy authority party. So finally, we told you about the policy carrying data, this new abstraction. Let me talk a little bit about performance. We measured the encryption and decryption performance of attribute-based encryption. We used a tablet representative of the types of tablets you find on the market today. On the right-hand side here at the top, you can see the SoC, the system on chip we used, which was an NVIDIA Tegra Jetson K1, which is sort of similar to most of the SoCs used in the generic tablets today. We also used an open source publicly available ABE library. This is a library written by John Bethencourt, and you can find more details about our methodology in the paper. And what the graph shows is the performance of encryption and decryption as a function of the complexity of the policy. In ABE, policy can be quite complex. On the x-axis, we measure the complexity of the policy by counting how many attributes the policy has. For example, requiring that GPS readings are single use only is one attribute. This goes all the way to 10 attributes, and these attributes have ands and ors between them. In this experiment, we only use the AND clause between the attributes. The y-axis is the duration of encryption and decryption in milliseconds. And this graph shows two things. First, the ABE's performance is quite adequate. It takes less than a quarter of a second to encrypt a very complex policy, a policy with 10 attributes, on a typical tablet today. And we believe that's not too bad. Second, decryption is faster than encryption. This is good because decryption is done in the cloud, and we were worried that the cloud needs to perform lots of decryption at the same time, and decryption needs to be quite fast. Now, decryption is faster than encryption, and that's good. Furthermore, know that decryption will be done on server class machines in the cloud and not on Tegra tablets like in our experiment. So that's an even bigger reason to get this number here down. So we told you a little bit about performance. Let me briefly talk about related work. PCD is inspired from an earlier piece of work we've done called Excalibur, which appeared at Using Security in 2012. Like PCD, Excalibur used attribute-based encryption to encrypt users' data and bind it to a policy. However, Excalibur went much further than PCD. It made use of heavyweight policy enforcement mechanisms, such as secure hypervisors, TPMs, verified protocols, and so on. Excalibur was representative of the class of systems that attempt to give you strong guarantees about the privacy of data technically. So the goal is to raise strong technical fences around the data. PCD is much simpler, and there is no policy enforcement required for it to actually be deployed in practice. So to wrap up, here are the conclusions of my talk. I hope I convinced you that mobile users face a privacy crisis, and that all current approaches sort of focus on this idea of putting strong fences around the data. This talk puts forward an alternative approach, which is to attach terms of service to data. PCD is one example of an abstraction for attaching terms of service to mobile data, and its advantages are that websites must interpret the policy before getting access to the data, or the cloud must interpret policies before accessing the data. There is an externally verifiable record of the policies of the cloud, of these websites in the cloud. The policies can vary from anywhere that are simple policy that are easy to understand to sophisticated policies, and it has adequate performance. The disadvantages is that this idea will not stop the cloud from restricting data, and that in order for it to work, it requires an out-of-band system that will detect the cloud's misbehavior. So that's the end of my talk. If you have any questions, I would encourage you to actually email me. Here is my email address, or any of my co-authors, Alec Wolman and Sharad Agarwal from Microsoft Research. Thank you very much for your attention. I hope you enjoyed this talk.